Hi everyone, so we're going to be looking at Unit 3.2 Trends in the Periodic Table. These are the objectives that we're going to look at. So in the periodic table, you know that elements are arranged in order of their product numbers, so it allows us to make predictions on the different elements. So because of the groups and the periods, we are able to predict down the group what is happening and across a period what is happening. So let's see the first trend, which is trend in atomic radius. So the atomic radius is actually the distance between the nuclei. It's the distance between the nuclei. So let's say this is the nucleus of the first element, and this is the nucleus of the second element. So the distance between these two, so that would be, so distance between these two is going to be 2 times the atomic radius, which means that the atomic radius, so radius is actually d divided by 2. So it's the distance between these two nuclei divided by 2. So this is what is the atomic radius. And if you look at the atomic radius across a period, you will see that the atomic radius decreases across a period and that the atomic radius increases down a group. So we're going to see why that happens. So as we go across a period, what happens? So let's see. So sodium, magnesium, aluminum, silicon, and phosphorus. What is happening is that the electrons are being filled in the same principal energy level. So here it's being filled in the third principal energy level, which means that the overall positive charge that is pulling the electrons is increasing. So we have more positive charge, so effective nuclear charge increases while the electrons are being filled in the same principal energy level, which means that there is an increasing effective nuclear charge that pulls the valence electrons closer to the nucleus. So as it's pulling it closer to the nucleus, they're going to get smaller across the period. So as you see here, the nuclear charge is increasing. So there's 11 protons, which is giving 11 plus, 12 protons giving 12 plus, 13 protons, 13 plus. So the nuclear charge, effective nuclear charge is increasing, while electrons, there's just 3 levels of electrons. So principal energy level n is equal to 3. That's the outermost energy level. So electrons are being filled in the same principal energy level while the positive charge is increasing, which means that the positive charge is able to pull the electrons closer to it, so it gets smaller. Now down the group, what happens is that the radius is going to increase, the atomic radius increases. And why this happens is that if we look down the group, so this is period 2, period 3, period 4, period 5. So as we're going down the group, so the period number is increasing down the group. So the shell that the electrons are being filled, the outermost shell, there is one more outermost shell. So we're filling electrons in a new energy level further away from the nucleus, which means that there's going to be more shells. So if we have more shells, means there is more shielding effect. Of course, the nuclear charge increases, but the thing is that even if the charge increases, the charge is not enough to pull all the electrons close to it, because the inner shells, more inner shells, act as a shield and prevents the positive charge from attracting the outermost electron shells close to it. So if you look at here, so here there's just one shell between the nucleus and the outermost electron. So this nucleus is able to pull it close to it. But here, the electron is shielded. All these inner shells act as a shield and prevent the nucleus from attracting it close to it. Plus, you're adding electrons in additional shells, so definitely it's going to get bigger. So here the explanation would be that in each new period, electrons are filled in new energy level that are further away from the nucleus. Plus, because you have more electrons in inner levels, this is going to cause a shielding effect that predominates over the effect of nuclear charge. Now, if you look at the atomic radius of transition elements, for transition elements, the radius is not going to change greatly. So there is no change across a period because the number of electrons is almost the same and electrons are added in the n-1 energy level. So what happens is that nuclear charge is definitely increasing, but when you look at the electrons, so the highest principal energy level is the fourth energy level, and all electrons that come in go in the 3D orbital, right? So as they're going into the n-1 energy level, which means that it's not going to affect the size as the number of valence electrons remain constant. So there is very little variation in atomic radius across the transition elements. There is a little change, but it's not considerate. Now, trends in ionic radius. Now, when we're considering ionic radius, we're considering the radius of ions, which mean positively charged particles or negatively charged particles. So if we're looking at positive ions are for cations, which means that they are for metals. And how do metals form positive ions? It is when they are going to lose electrons. So they have less electrons than the atom, and because they have less electrons but the same number of protons, what happens? So the positive is going to be able, so the positive charge in the nucleus remains the same, but instead of, let's say, sodium element has 10 protons, 11 protons, 11 electrons, but sodium cation has 11 protons but 10 electrons, which means that this 11 protons will be able to attract this 10 electrons more than it would be able to attract this 11 electrons. So it's easier for it to attract it. So what happens is that it's going to become smaller because the electrons are more strongly attracted to the nucleus. Isoelectronic positive ions decrease in size across a period as the number of electrons remain constant, but the number of protons increase. So isoelectronic positive ions means that ions that have the same electronic configuration, which means the same number of electrons, which means that after they lose the number of electrons, they have the same number of electrons, which is going to be equivalent to the number of electrons to the nearest noble gas. And if you look at these elements, so sodium, magnesium, aluminium, they're going to reach the electronic configuration of neon, which is the nearest noble gas that has 10 electrons. So they're going to lose electrons from 11 to 10, 12 to 10, 13 to 10. So all these elements, they have the same number of electrons when they form cations, and the number of protons remains the same. So there is an increase in positive charge. So because we have more positive charge but the same number of electrons, it's going to get smaller. So there is an increase in effective nuclear charge that is going to pull the valence electrons closer, which means that the positive ions are going to get smaller across a period. So this is what you see, they get smaller. But if you look at negative ions on the other hand, so this is for non-metals, when non-metals are going to gain electrons to form anions. Now since we're adding electrons here, so we have the same number of protons but we are adding electrons. So the added electron is going to cause repulsion between the valence electrons. So this is going to cause them to get bigger. So let's say chlorine had 17 electrons, and when it's going to gain 1 electron, so there's 18 electrons, these 18 electrons will tend to repel each other. So if they were arranged, let's say we find a very simplistic way of arranging these 7 electrons. When we add 1 electron to it, what happens is that they will want to spread even more out because there will be mutual repulsion between them. So it gets bigger, right? So there is repulsion between the valence electrons, but there is the same nuclear charge. Now isoelectronic negative ions, which means negative ions that have the same number of electrons, as we're moving across a period, so what is happening? We have an increase in number of protons but same number of electrons. So definitely there's going to be a decrease in ionic radius. So nuclear charge is going to increase, effective nuclear charge increases, but number of electrons remain the same, so it's going to get smaller. So if you look at this, so let's compare phosphorus, sulfur and chlorine. If they are forming the anion, so it will have the same number of protons. So as you can see, the number of protons is increasing across a period, but the number of electrons remains the same because they are isoelectronic ions. So for the cation, the number of electrons is the same, but the proton number is increasing. Effective nuclear charge increases, which means that there's going to be smaller ionic radius. So that's it about the trends in ionic radius.